Hello, this is the lesson video for lesson 5 of module 1 of the EngageNY Algebra I curriculum. We're going to jump to example 2 of these notes. Example 1 and the opening exercise we'll do in class, but this is just to kind of get us started on these systems of equations, graphing stories. So for today, we are going to be looking at two graphs on the same set of axes to try to figure out things about stories when they're happening simultaneously. So it gives us a story. So Duke starts at the base of a ramp and walks up it at a constant rate. So we've got a ramp. Duke is starting and he's walking up at a constant rate, and it tells us actually his rate of change. So this is going to be 3 feet every second. That's our slope. 3 feet per second, that's a good slope. So just as Duke starts walking up the ramp, Shirley starts at the top of the same 25-foot high ramp. So we know that that's 25 feet tall. And she begins walking down at a constant rate. And again, it tells us her slope, her elevation decreases 2 feet per second. So she's moving a little bit slower than Duke is, okay? So he's moving at 3 feet per second and she's at 2 feet per second. So sometimes it's helpful just to have a little drawing like this. So it says sketch two graphs on the same set of elevation versus time. It's always y versus x to represent Duke and Shirley. So I actually went ahead and made a set of axes for us. So if you need to pause the video, grab a piece of graph paper and make some axes. I ended up counting by twos because I know I have to get to 25. If you wanted to count by threes, that's fine too, as long as we have a good incremental change up to 25. If you want to count it by ones, that's fine. You might need a bigger graph. But let's sketch these two graphs on the same axes. So I'm going to start, usually when you do systems of equations, so two or more graphs on the same grid, do one at a time. So I'm going to start with Duke because I think Duke starts at the base of the ramp. So he's starting here. He's at 0 feet elevation at 0 seconds, and he's walking up at a constant rate. So he's going to be going up the ramp, elevation increasing, and they actually give us a slope, so we need to be conscious of that. So it looks like his, we said, was 3 feet per second. So the way we set the graph up should lend us pretty nicely. So I'm just going to kind of go across the graph until I get up near the 25. So he increases 3 feet per second. Notice I counted by ones for seconds. So from here, he increased 3 more feet per second. Now it'll be up to 9. So sometimes you're in the middle of the grid lines, and that's okay. So let's keep going. 3 feet per second. It's at 15. 3 feet. 18. 21. 24. And the next should be, he should be at the top of the ramp somewhere in between here. So I'm going to go ahead and use a straight edge to connect those points. Perfect. So that's Duke, and I'm going to go ahead. Now I can see what Shirley's looks like. So we said that Duke was going 3 feet per second, which is a little faster. So we hopefully will be noticing that Shirley's slope is a little bit flatter. Not by much, but she's only going 2 feet per second. And she looks like, the story says she starts at the top. So her elevation at time 0, she's already here at 25. So if she's at 25, she is decreasing at 2 feet per second. So down, I'm going to be at 23, 21 after another second, 19, 17. And then you can see here when we get to that 15, and you can even put a little star on it. That's where they're intersecting, is at that 5:15. And then keep going with Shirley. So she decreases 2 feet per second. Now she's at 9, 7, 5, 3, 1. Oh, Did I count too much? We were at 9, 7, 5, 3. Then she's at 1, and then eventually she'll get to the ground. So I'll use my, notice this is slightly lower slope. Duke's line is a little bit steeper. I'm gonna use my straight edge to connect these as best I can. So I followed the directions. Now I can see that this point, this was point 515. So that points of intersection on systems of equations tell us this point 515, it's on both of the lines at the same time. So let's take a look back at our questions here, and we'll flip back and forth to the graph. So we sketch the two graphs, done. That's on graph paper. If you actually tried to do it here, that's totally fine. This is just a little bit more exact. So what are the coordinates of the point of intersection? So we actually already found that, the two graphs. So the point of intersection we found was 515. At what time, notice which axis is time? That's the x-axis. So at what time do Duke and Shirley pass each other? That would be after 5. And we can say even after 5 seconds. They pass each other. So that's what this point on the graph means. So when you've got equations that are describing something happening, that point of intersection is where they are at this elevation at this time, and they just happen to be in the same place. That's what this means. So now, if we write down these equations, so think back to how do I write an equation of a line that represents Duke's motion? So what do we need for a line? We need a starting point, and we need a rate of change. In other words, we need a y-intercept. So where do we begin? How fast did I move? Those two pieces of information can give me the equation of the line. So let's do Duke first. So Duke and Shirley have their own equation. So let's just focus on one at a time. Let's focus on Duke. So we know elevation, this is our y-axis. So an elevation, Duke, his elevation is equal to, how do we write a line? Where did he begin? Well, we know he started at 0, so we don't typically write 0 plus something else. We can just kind of omit that. So he started at 0, and what was his rate of change? He was at 3 feet per second. 3 feet per second. Could I put plus 0 at the end? Yeah, you could. We don't usually do that, but you could. And then equation of Shirley's line. Shirley, her elevation, so her y value was equal, where did she begin? She started at the 25. So if we're writing these in y equals mx plus in slope-intercept form, we've got slope and y-intercepts. So I have that. Could you put 25 plus, what is her rate of change? 2 feet per second? Could you put 25 plus 2x? Absolutely. It doesn't really matter. As long as that slope, her rate of change, is connected to her time variable, her x value. So 2 feet per second, and she started, ooh, actually I'm missing a little something. So we need to show that she's actually descending. So if she's going downward, if I left it like this, this would show that she's moving up. But she's actually going down, so I need to make that slope negative because that line is decreasing, okay? And then we can show that the coordinates of the point you found in the question above satisfy both equations. So if we think, if this 515, if we were to plug in x and y, 3 times 5 is equal to 15. That's a, check that off. How about this? -2 times 5, that would be -10 plus 25 is equal to 15. So notice that the x and y values both they make each equation true. You're not going to get a false answer, okay? And I will attach an image that shows these coordinates matching each other as well. That shows that. Actually, I can just show that right now. So for Duke, we've got coordinates of the point you found above. We can say y value 15 is equal to 3 times 5. That's definitely true. 15 equals 15. We can also show that 15 equals negative 2 times the x value plus 25. So that's negative 10 plus 25 equals 15. Absolutely correct. So this was our very first introduction to our systems of equations graphing stories, and we'll get back to systems of equations in about a month or so. So thank you for watching.